Так, Борис Леонидович, все нормально? Посмотрели? Только вам звук теперь надо включить в себе.
Так,
Ага. О,
в общем,
отлично.
слышно меня, да?
Угу. Единственное, у вас сейчас, ну, вот, камера, она, видимо, задняя, направлена на стол куда-то.
Так. А до этого было нормально, да?
Может, переключилась там как-то.
А презентация нормально?
Презентация нормально, презентация отлично. Можно камеру, в принципе, выключить, если...
Выключить участники, чат, новая демонстрация, паузы, комментарии, дистанционное приложение. Я не вижу, как тут переключать. Дополнительно. Записывать на этот компьютер.
Не-не-нет, у вас вот там, где начать видео, это значок рядом с микрофоном, видео. Там есть
Так,
такая
это надо
маленькая
выйти.
стрелочка.
Так, это надо выйти из полноэкранного режима тогда.
Ну, можно выйти, да. Мгм.
Так, а как это сделать?
Escape нажать.
Escape. Escape у меня не работает уже. Так, сейчас попробуем по-другому. Просмотр всех слайдов.
Не-не, это сейчас он мозаику сделает. А вот завершить внизу, там, завершить показ слайдов сделать.
Так, совершить показ слайдов. Так,
Мгм.
и вот где вы говорите?
Вот рядом с микрофоном, где вы звук включали.
Так, вот это, да? Режим чтения здесь написано.
Не-не-не, нет.
Слайд-шоу.
Закройте сейчас демонстрацию совсем.
Так, новую демонстрацию нужно нажать, да?
Нет, отменить демонстрацию, завершить.
Ну вот она говорит, вы запустили демонстрацию, здесь новая демонстрация. Пауза демонстрации, комментарий, чат, дистанционная. Ну,
М.
наверное, новая демонстрация.
Пробуйте.
Да, вот так вот. Так? Так, и дальше что?
Не, у нас ничего не поменялось.
Так, так.
Так, ага.
И что?
Сейчас, секунду. Я вижу просто у вас рабочий стол весь. Мгм.
Так, выключить, остановить видео. Участники.
А вот остановить видео, где у вас?
Ну, что остановили видео?
Вот так остановлено. Мгм.
Что дальше?
А,
Экран-то есть?
экран есть. Теперь можно презентацию опять развернуть на значок тот самый. Да, вот это. Нажать. О, отлично.
Да? Ограничимся. Без моей персоны. Без видео моей персоны, да?
Да. Так, только сейчас у нас появилось почему-то маленькое окошко.
Да. Как его убрать?
А ткните на большую просто окошко.
Так, всё.
Мгм. Да, все, отлично. Мгм. Ну, я тогда предлагаю начать. Сейчас я представлю. Так, so, оп, just a moment. So, dear colleagues, today we will continue with the lectures that will be given by Professor Boris Zhukov from Institute of Nuclear Research from Troitsk. Professor Zhukov, the floor is yours, please.
Так, ну, меня слышно, да?
Слышно? Можно начинать, да?
Вы кончили, да? Представление.
Да, можно начинать. Мгм.
So, greetings to the participants. In this first lecture, I would present some review of production of radionuclides by charged particles the first part of my presentation, I'll tell you a few words and show some slides on general situation with production of medical radioisotopes in the world and in Russia. The second part of the presentation, we shall discuss with you some securities and some problems for production of medical radionuclides in on accelerators of different types. And then I shall present some example based on our experience in our institute, because our institute is not the main producer, not the main producer of medical radioisotopes in Russia, but in the sense of development, we have very many important achievements. So this example will be important for scientists, first of all, not for people who are involved just in radioisotope production and application. So, the first slide. Over 10,000 hospitals in the world use now medical radioisotopes, and about 100 different nuclear medicine procedures are used. You see in this slide that 49 million procedures each year are performed. And the main application of medical isotopes is, of course, in the United States of America. The second region, very important region, in Europe. And in Europe, we have about 1,500 nuclear medicine centers and about 10 million procedures of patients each year. And an important trend in the past years is that more and more accelerator produced radionuclides are used. Of course, meanwhile, the main production is based on nuclear reactors, but accelerators are more and more important. In this slide, in this slide, this is a very old slide, and demonstrating some trends and prediction of development of application of medical radionuclides. You see that it is growing enough fast, both in diagnostics and therapy. But the trend of the last years is to use more and more therapeutical radionuclides. It seems even more important than diagnostics, because many other methods of diagnostics are efficient, but it is difficult to compete with nuclear medicine in therapy. Some radionuclides are very efficient, and other methods cannot provide such success. In this table, you can see radioisotopes which are used in Europe. The first part of this list, of this table, are isotopes which are used very often. You see, current consumption is about 10 millions, thousands of procedures, 10 millions per year. But, for example, with technetium 99 M, and this is the most popular radionuclide produced on nuclear reactor. About 80% of all procedures are performed with this radionuclide. But future consumption is not growing, is not predicted to be growing. The same situation, very similar situation with second very popular isotope, fluorine 18, which is used for PET diagnostics. It is extremely popular, over million procedures per year in Europe. This is Europe. But, and people propose some growing, but not too much. You can see also other popular radionuclides, iodine 131. This is blue is reactor isotope. Then also enough popular isotope iodine 123. All these yttrium, radium, all these isotopes are very important, but the growing is not too much. That means that other isotopes are more interesting for development for scientists. The second group are radionuclides that are surely clear that they will be very popular in the nearest future. This is gallium-68, which is produced on accelerator, and it is a generator isotope. And you see, in spite of comparably low consumption now, the growing is expected up to 1 million per year in Europe. Also very important, of course, lutetium, but it is a reactor isotope, and several other isotopes. For example, copper 64, you see this is very interesting isotope. It is used both for diagnostics and therapy, and now it is used only in small amount for investigation. But it is proposed that the amount of production and application of this isotope will be growing fast. The same with zirconium 89 and PET isotope iodine 124. But there are also isotopes which have a very limited application now, just in clinical trials in Europe. But one can be sure that these isotopes in the nearest year will be also used in many applications. First in this list is rubidium-82, and I am glad to announce that our colleagues and collaborators in France already got some marketing authorization, and thus in the beginning of the next year, this isotope basing produced from a strong fumated generator will be regularly produced in Europe and not only in the United States. The second important therapeutical isotope is actinium-225. It is also used now in limited amount in clinical trials, but people are sure, and there was also a special conference in IAEA devoting to this isotope and production and application, because it is demonstrated very high efficiency. Also, very interesting isotope is astatine 211, used for therapy. It is also alpha emitter, as well as actinium-29, and some other isotopes are also prospective. So if we are speaking about science, so we should pay attention mostly, to my mind, mostly to the second part, and especially in the third part, because the first part is well developed up to now. In particular, technetium, there is a shortage of production of technetium in the United States. And let me remind you that the United States is the leader in nuclear medicine now in the world. But they demonstrated that other isotopes should be used more and more, and technetium is not produced so much as it was recently. But still, it is about 80% of all procedures performed in nuclear medicine, especially in diagnostics. In this table, it was Europe. In the United States, there are some different priorities. So in this slide, you can see which isotopes are predicted to be used in nuclear medicine in the near future. This is the so-called second wave of radionuclides. Deuterium, for example, is used already in the United States, and even tin-170M is used, but only for dogs. But it is proposed that other isotopes, the so-called this third wave in the United States, will be produced in reactor and accelerator facilities and used more and more in nuclear medicine. So this slide just demonstrates that accelerator produced isotopes are very popular in scientific developments. Isotopes produced in this and this slide. This is a number of publications. this is publications about isotope production of for isotopes, for reactor isotopes, and this accelerator isotopes. You see, accelerator produced isotopes, publications, number of publications for accelerator produced isotopes are growing much faster than number of publications for reactor isotopes. And the same situation with citations. Yes, citations more and more also in reactor isotopes, but in accelerator produced isotopes, it is a real boom because a number of publications are growing very, very fast. In this slide, you can see where accelerators used for production of medical isotopes are located in the world. Of course, it is the United States of America, Europe, Asia is not too much, but of course, Japan and South Korea have enough achievements in this field. More and more accelerators in China, and if to compare different countries, for example, you can see that in the United States there are more than 250 accelerators which can be used for production of medical isotopes. But in Russia, only 60 isotopes, 60 accelerators is not too bad, taking into account the difference in population. So per 10,000 of population, the difference is only twice. So Russia is well equipped with accelerators, which may be used for production of medical isotopes. But unfortunately, this does not result in the development of nuclear medicine. I'll tell you later. In particular, you see nuclear facilities where nuclear facilities around Moscow, where medical isotopes and radiopharmaceuticals may be produced. First of all, it is town Obninsk, and it is about 100 kilometers from Moscow, and there is a big institution for where the first nuclear power station was constructed, and there is also another institute where nuclear reactor for producing of technetium and molybdenum-99 and a number of other isotopes. And there is also a very successful private company, cyclotron, and they produce the main accelerator isotopes in Russia. I'll tell you a few words later. In our institute has a big accelerator, I'll tell you later, and we also started production a number of medical isotopes for application in Russia and abroad. And there are also some other facilities, but now the production of real production of medical isotopes is very low, but the development are in progress. In these facilities, Kurchatov Institute, in Tver, Dubna, and Protina. So let us speak now about the plan of procedure, how to begin production of accelerator isotopes. The first item is evaluation of physical, chemical, biological, and medical properties of radionuclides and its demand. First of all, we should look on physicians, on medical community to understand what do they need first of all. The second step is the choice of nuclear reaction. I'll tell you later what do I mean. The third item is theoretical calculations of cross sections and production yields. Then the choice of available accelerator, because there are many different accelerators, and making a correct choice is extremely important. Then experimental measurements of cross sections and production yields. Then target redevelopment, because if you have a very good yield with small targets with low beam intensity, this doesn't mean that it works with high intensity beam. Then experimental investigation of target stability, then development of radiochemical separation. This is the most interesting and important for radiochemists. And afterwards, when you have a developed chemical procedure, you should evaluate quality, because even if you produce isotope of good yield and isotope which is needed very much in the world, probably your work may be in vain if the quality of the product is not enough high produced by some method. Then production of test samples for a customer, then radiopharmaceutical development and test, then medical trials, and then development of logistics of productions and transportation, containers, what kind of transport is used, etc., etc. This is also a very important item. Then evaluation of the production volume, pricing, business model, and at last only item number 15 is development of high-level production schedule. So you see that beginning of the real production of medical isotope is a big deal. And an experience of our institute, our group, has demonstrated that we can pass all these items from the very beginning up to the very end. That means wide application of medical isotopes, but we should interfere in each of these items. If you consider that, for example, that you need also development a good method of production, but do not discuss, do not investigate, for example, business model, any possibilities of transportation, it doesn't work. And your scientific development means nothing. So you see how long way it is production of medical isotopes. Now let us see what kind of accelerators are used for for production of medical isotopes. First, the a light particle accelerated particle is electron, but though this is the first line in this table, it is so far not very important in the world. Electron accelerators are not so much expensive than other accelerators, and with using accelerated electrons, you can produce gamma rays of high energy and also neutrons. And unfortunately, right now, only developments are well for production of molybdenum 99, actinium 225, but there is no regular production yet. The regular production, it is the next line, it is the so-called medical cyclotrons, usually used for PET. I shall tell a few words about this direction. Then low energy accelerators, that means about from 15 or 20 MeV protons up to 30 MeV protons, 40 MeV protons, and the most amount of medical isotopes are produced by this way. Then middle energy accelerators, which is an extremely prospective direction, and we in our institute work for middle energy accelerator production. Then high energy accelerators. It was popular in the past, but now it is not very popular and used mostly for investigations. Then you can use also accelerators for neutrons and alpha particles, and also just for investigations, accelerators of heavy ions. Well, the first important moment is what kind of accelerator should be used in order to produce this or different medical isotope. You can see in this slide the advantages and disadvantages of production of medical isotopes on different type of accelerators. If to use low energy accelerators, usually you have a high cross section and also thin targets, and providing a good cooling. So this is the most easier way to produce accelerator radionuclides. but sometimes is not the best. But up to now, this is the main way of production, because not all isotopes may be produced on such nuclear reaction with emission of from 1 up to 3 neutrons. And usually you are obliged using enriched target material, which is expensive and not always available. With high energy protons, you can produce a great number of radionuclides. This is the direction of proton beam irradiating several targets in this direction or in this direction. But in this case, you have low cross section. However, the production yield may be enough high. But the disadvantage is that too many isotopes are produced in this way. And usually chemistry on separation and purity and quality control is a big challenge in this case. And a very good compromise is using middle energy protons from 70 to 200 MeV. It is high cross section and enough cooling and small amount of impurities. In this slide, you can see the item concerning the cross section measurements. This is calculated cross sections calculated by different models. ELICE, TELIS, in our institute, cascade evaporation fission model is developed. You can see that at low energy, you can produce isotopes in this kind of nuclear reactions, and at high energies, you can produce different kind of radioisotopes which cannot be produced at low energies. And as example, for cross-section measurements, this is our main product, which we produce in our accelerator, is strontium 82 on metallic rubidium target. Probably I'll tell you a few words if there will be enough time. So, and back to the item of medical cyclotrons. Medical cyclotrons are mostly used for production of PET radionuclides. And one can irradiate different kind of targets to produce these short-lived isotopes, which emits positron annihilates, and positron emission tomography is very efficient for diagnostics of many diseases because gamma quantum are measured in coincidence. And other isotopes which are produced in low energy accelerators is gallium, is germanium-68, providing generator of gallium-68. and strontium 82 providing rubidium 82. So see in this table what targets and are used for producing of these short-lived isotopes: oxygen, nitrogen, carbon, and fluorine. Fluorine currently is the most important isotopes used for production mostly of fluorodeoxyglucose, which is extremely popular for diagnostics of any kinds of cancer disease. So accelerators used for this production sometimes are located in hospitals with this energy. If you have a high energy, usually these accelerators are located in scientific and radiopharmaceutical institutions, and then short-lived isotopes are transported to clinics. Of course, it is difficult but quite possible to transport fluorine, about 2 hours half-life. But if you have a very well organized system, you may transport also even these two isotopes. This oxygen, of course, not possible to transport. In the United States of America, where I was many times, so they succeeded to transport these isotopes too. So this is slide where new PET cyclotrons are installed for production of fluorine and other short-lived radionuclides. And here you can see how many procedures with fluorine are approved in different countries. In the United States, this number is about 900, in Canada 200, but in Russia only 11. You see the difference is very bad. So now the second line is production of isotopes on low energy accelerators, and example, a good example, as I told before, it is cyclotron company in Russia. They produced a number of medical isotopes very successfully, and providing many of them both abroad and to Russian hospitals. Cyclotron is the first and the best medical isotope accelerator facility in Russia, but there are possibilities also in Kurchatov Institute, in Tomsk Polytechnical University, Open Institute in St. Petersburg. This is cyclotron in Tver, which belongs to Minister of Defense, therefore is not so available for real production. And at last, our institute. So, which isotopes are the most popular to be produced in the on accelerators? Thallium-201 used mostly for cardio diagnostics. Iodine-123. In thallium, they irradiate enriched thallium, and chemical isolation of lead, they can get a pure thallium 201 decaying from this. So some chemical procedures are developed for this deal. Iodine is a volatile product that it is used usually is production and recovery based on high volatility, and it is produced either with enriched xenon or with tellurium oxide, and at last it may be produced on sodium iodine targets at middle energy. So also important isotope, which is medical isotope, which is produced on low energy cyclotron, is germanium 68. Cyclotron company have good successes. This isotope used both for calibration of PET scanners as well as preparation of generators of gallium 68. This is positron emitter used in PET diagnostics. So, unfortunately, we have already not too much time. How much time do we have to complete the presentation?
Борис Леонидович, для вас можно хоть сколько?
We are not limited, yeah? No, this is very well. So, these are prospective isotopes produced on accelerators, which can be used for theranostic, both for diagnostic and therapy. This is is a novel trend in nuclear medicine, when you can at the same time treat a patient and to observe how does it works with PET or SPECT scanners. So first isotope is tin 170M, and we produce these isotopes in copper, arsenic, lead, and for therapy only is used actinium and radium-223. Now, let me tell you about the next branch of accelerator produced isotopes is production and intermediate energy protons. At this point, only 7 facilities in the world are involved in this kind of production. This is Los Alamos National Laboratory, Brookhaven National Laboratory, also in the United States. Then Triumph, a very nice facility in Canada, in Vancouver. Our institute, IFEMBA Laboratory in South Africa. New facility, what does it mean new? Several years, is Aeronax in Nantes, France, and also new commercial facility in Zevakar, and also there are several other facilities which are already installed, and soon will start the production of middle energy. This is slide for Los Alamos, accelerator of Los Alamos National Laboratory. They have a huge linear accelerator, and the beginning part of this accelerator has a beam output at the energy about 100 MeV, and they produced a number of important isotopes on this kind. This is Brookhaven National Laboratory. They have also LINAC, and also produce medical isotopes beginning from the end of 80s. And this is Triumph, and this is Aronnax, French facility. They use cyclotron produced by well-known company IBA from Belgium. And also this is Zevakov facility. All these facilities were have a good achievements, and we are proud that we participated in this development of these installations. So what are problems if you use middle energy protons from 70 MeV to 200 MeV? You have to use thick targets, that means a good yield, but also you have a target problem. So you should have a very good cooling target, and also the material of the target should be not only temperature stable, but also they should not react with cooling water. For example, if you use aluminum target, it is destroyed under the beam because the cooling water reacts with aluminum. This is not really water, but water containing peroxide, hydrogen peroxide, and many radicals, ions, which is much more active than just pure water. And see what may happen with even with graphite or molybdenum target. So already done. This is our facility in our institute. This is Troitsk, not far from Moscow. Now it is already a part of Moscow, and we have a huge underground accelerator, half of a kilometer long, and we have beam output at the energy about 160 MeV, and we installed a good facility at this 160 MeV beam for producing these medical isotopes. This is our target cell. This is how we measure cross sections, so many foils with different energies. This is a list of isotopes which are produced, really are produced in our facility. And unfortunately, we do not have ourselves radiochemical facilities for isolation of the produced isotopes. So we have to ship irradiated targets in other facilities where they perform chemical procedure of radiochemical separation based on our methods. This is Los Alamos in the United States, Obninsk IPP, Mayak, St. Petersburg, and some other places. So it was very good, successful collaboration with Los Alamos, first of all, and about 3 or 400,000 of patients were treated with isotopes produced at our facility, and our technology developed at our facility was also installed in other facilities. So far, the number of patients is about 2 million or even more developed by our methods. This is our main target of metallic rubidium in stainless steel installed in the target cell. And this is investigation of the temperature distribution during irradiation. This is our future proposal for online production of strontium from cyclic metallic rubidium. No time. This is the scheme of production and transportation of our main product, strontium 82. So metallic rubidium we received from Murmansk region in Russia. Then we irradiate in our target. Then we ship it to Los Alamos National Laboratory. Then Los Alamos extracts strontium and ship it to New Jersey in the United States to produce generators, and then distribute all over the United States and all over the world. But now we developed also a different line with Russian institutions on. Now also, as I told you before, France also succeeded well with this method. And this is distribution, production cooperation with our American colleagues. This is another isotope which I mentioned before. This is tin 170M. This isotope may be produced at now accelerator with middle energy protons, and the best target is containing antimony. Antimony itself is a bad target for irradiation, so we invented a compound and target of titanium antimony, and this produced isotope is very well both for diagnostics and therapy, because it is gamma rays of this energy, which is close to the most popular 140 MeV energy from technetium 99M. So it may be used in regular PET facilities, and at the same time it emits уже electron. This is not beta particle, but уже electrons. They have a very low energy and maybe used for targeted therapy. So this is cross-section measurements of this production of this radionuclide and impurities. There are some other isotopes produced by this way. It's no time to describe all of them, but the most important is now for us is producing actinium-225. We discovered that it may be produced on our accelerator and also in Brookhaven accelerator with energy more than 100 MeV with very high yield, and so in these nuclear reactors. So in this way, we can, in 1 or 2 weeks, we can produce actinium-225 as much as it is produced in the whole world per year. So we hope to start regular production soon, and development are completed. So different targets used for actinium production, and this is comparisons of potential of production of INR for Kevin National Laboratory, for Salmos National Laboratory, and France. So this is our future of production. And let me finish this presentation with some problems which are to be solved to have efficient production of medical isotopes, especially in Russia, but also in other countries. So the first and very important problem is to overcome agency barriers, because the most important nuclear facilities in Russia belong to Rosatom. Rosatom is production agency, and it is not very well for development as well as Russian Academy of Sciences, which we belong to. So collaboration and not hard competition should be developed in order to have a really good production. So the second item. You see, in the world, there are big, very powerful companies, such as General Electric and Curium, which have a large scale production. So they can they can invest some funding for development of new procedures. But in most countries, and both, even in the United States and in Russia, in China, everywhere, governments should provide funding for this kind of development, for fundamental development first, and believing that sooner or later fundamental developments will provide effect of successful medical application. This is the second item. So, and the third problem, the third item is how to make choice of different suggestions, different directions. Unfortunately, in our countries, the choice is determined by bureaucratical procedures, but not by scientific communities. And they are used as experts. So scientific expertise is not enough for making decisions. I believe that scientists should, which are involved in production of medical isotopes and developments of radiopharmaceuticals and in application of medical isotopes, should make a final decision what to produce and where to invest government money and where do not invest. So to improve the logistics system, this is clear. The transportation and distribution of medical isotopes are extremely complicated thing, especially when you have short-lived isotopes. So both technical and documentation should be provided very well. And bureaucratical regulations should be reduced. Otherwise, no any successful developments can be done. Those people who are restricted by bureaucratical procedures actually have no achievements in production of medical isotopes. And the last item is provide an education of highly qualified experts, specialists. So this school, I believe, will work and will provide some success just in this item. Thank you for your attention.
Thank you. Any questions? So, but from me, question, if we compare production of radionuclides with the accelerators and nuclear reactors, what are, let's say, advantages of charged particles?
What the production volume?
Production by charged particles, by accelerators, and by reactors.
What do you want to compare? The activity or money or what? Both?
Both, yeah.
I would say that the money is now already close to 50-50. Activity is much higher activity is produced in nuclear reactors. I told that only molybdenum 99 providing technetium 99(2) is 80%, and there are also some other isotopes, but these technetium and also traditional isotopes have a high production volume, but not as too much efficiency for diagnostic and therapy. So small amount of isotopes produced on accelerator particles really it appears that are more efficient than big amount produced on nuclear reactors. And also, if we speak about money, it is also very complicated deal because practically all nuclear reactors are supported by the government, and also some accelerators are supported by the government. But regularly operating of small accelerators is cheaper than nuclear reactors. Therefore, if there is no government support, maybe reactor isotopes wouldn't be so cheap.
Okay, thank you. Yeah, more questions. Just a moment.
Thank you. I would like to ask if, okay, there's this technique of nuclear transmutation. There's this way to treat nuclear waste by using the ADS. Are there some radionuclides produced by this technique, and what are those radionuclides?
So about ADS system, accelerated driven system, yeah, in nuclear reactors.
Yes, there are some projects for of this kind, but it is not still well developed. Maybe in future, when it will be well developed, we can tell is it efficient or not. Now it is not clear yet. will it be efficient or not? But nevertheless, as I told you in the end of my presentation, that the government should invest in new developments, including this branch, because nobody knows exactly will it be efficient or will be not efficient. Of course, in the proposal, you can write everything that it will be very, very efficient, but really, unfortunately, not all the new developments are successful.
Okay, one more question. Yeah. Second.
Thank you. Thank you so much for the presentation. There were quite a few institutes mentioned with some very high energy accelerators. And I would like to ask if in Russia there are any accelerators which are capable to produce high enough energy to induce spallation reaction. And if so, is the production of isotopes via this route is explored or not? Thank you.
Practically the main accelerator of this kind is accelerator at our institute right now. There is an accelerator in Dubna and with proton energy 680 MeV, but they have a very low beam current, only few microamps. And our accelerator, we operate routinely on beam current about 120 microamps. There were also some projects to produce radionuclides on 70 MeV machine bought from Belgium, but unfortunately this project failed so far. And there is also a facility in near St. Petersburg, and they have proton accelerator with energy 80 MeV. Unfortunately, it is a very old accelerator, and not for accelerating of H minus as usually of this kind, but old proton accelerator. And they announced their projects to produce the same isotopes that we are already produced, but the production yield is much lower, and really beam current is much lower than we have, because they can operate for some time at 100 microamp, for example, but only a short time. And we can, because activation of cyclotron is too much. So at this point, our accelerator is the only facility that can produce medical isotopes on middle and high energy protons, unfortunately.
Okay, thank you. One question from online. So in your opinion, for the developing countries, what would be the better choice, reactors or cyclotrons for developing countries?
My recommendation is for developing countries is to develop small, low energy cyclotrons, not middle and high energy accelerators, and not reactors.
Okay.
These, reactors, all other isotopes may be provided by other countries, because this kind of developments is very, very difficult and needs tens and tens of years of experience. And better to participate in collaboration in, for example, in radiochemistry with European or American Americans, or with Russians. And it is reasonable for them to have small cyclotrons on 15 MeV, maybe 20 MeV, maybe even 30 MeV, but not high. The only developing country which has good success in this direction is South Africa. And also there are some real projects, but they have not started yet. Project in South Korea and in China, but they haven't started yet. South Africa started many years ago.
Okay, thank you. Any more questions? If not, then thank you again. Thank you for your presentation.
Thank you for attention.
So now we will have the lecture that should be on Monday. Okay, should be fine. Yeah, okay. Okay, should be better. So you already had a presentation on Monday given by Peter Matveyev about the interaction of ionizing radiation with matter, and it is quite important because any nuclear reactions, any action of our radionuclide on our tissues, on or on material of detector, doesn't matter. All these interactions, they're based on the principal mechanisms of action of ionizing radiation. What are the consequences? What are the results? What are the mechanisms of this interaction? Either it is electromagnetic waves interacting with our material, or it is charged particles, or it is neutron, or whatever. So if you know the mechanisms, how different types of ionizing radiation interacts with your material, so you can guess what will be the result. And radiation safety, of course, also is based on these principles, on these mechanisms. And why the radiation safety is important? Because, of course, if you misuse or use incorrectly the ionizing radiation, if you don't know about the doses, about the consequences, about the results of the action of ionizing radiation, then it will be dangerous or hazardous for you and for patients and for other people. Unfortunately, it is real stories when due to the miscalculations or due to the failure of equipment, radiological equipment, people got much higher doses than it was allowed, and they get some different injuries. It can be direct hurts like skin damage or cataract or some other process, the hair loss or some problems with stomach and etc. Or it can be very prolongated actions like cancer diseases that actually these results will be not immediately will be seen, but only after a few years. Yeah, so it's in prolongated action of ionizing radiation. And interesting that in the beginning of 20th century, 100 years ago, let's say, the negative action of ionizing radiation was not known. When radioactivity was discovered, so it was in 1896, let's say 125 years ago, it was like a miracle, because at that time people already knew about the X-rays, about the some let's say magic rays that can penetrate through the matter, and you can obtain some pictures of the bones or other materials that are located inside the body. So it was really like a miracle and like magic. And when Henri Becquerel discovered that uranium, and later Marie Curie and Pierre Curie discovered that radium, polonium, and other elements also can produce these X-rays just by their own, without any electricity or I don't know, sunlight or whatever, without any external action on these salts, on these uranium salts, just by their nature. Uranium salts and radium and polonium, they can irradiate this unknown rays or some magic, I would say magic rays at that time. And of course, then these elements were discovered, their presence suggested as a it was thought that these elements has some healing properties, and they were added in many all-day, let's say, products, starting with just drinking water. It is quite famous, radium water for drinking. It was like small bottles that you can buy in pharmacies, or it can be a bit more expensive equipment. This vessel that you put inside the ampoule with the small amount of radium, and you saturated the water with the radium, and you can drink it in your home, so without going to pharmacy. Or it is chocolates or some cosmetics, bath salts, or even toothpaste. I like this advertisement because for me it is a good example that even 100 years ago the people who make advertisements were quite clever, because you can see that they used the real name, real doctor named Alfred Curie. So they said that this receipt is produced by Alfred Curie. And of course, the family name Curie was quite famous. Nobel Prizes of Marie Curie and Pierre Curie. And this family name was very famous. And of course, people trusted to this family. But the story that Alfred Curie has just the same family name, so he was not a relative to Marie Curie or Pierre Curie. He was just the man with the same family name. So, and the people used it to make the advertisement. And unfortunately, all these unknown negative effects and I would say wide applications of natural radioactive sources resulted in I don't know, many or few, let's say some deaths. Some of them were very famous. Of course, first one of the most famous is Marie Skłodowska-Curie, who died in when she was 67 years old, so not very young, but still the reason of her death was the negative action of ionizing radiation. Another scientist was Clarence Madison Daly, who was assistant in Edison's lab, and he worked a lot with these X-ray tubes, with these vacuum tubes that are glowed when high voltage was applied. And as far as he worked a lot of with hands with these tubes, a lot of doses were given to the hands, and first his hands were amputated, and then he died due to aplastic anemia. And another example, not scientist, but quite a rich man, Eben McBurney Byers, who was a rich man. So he was able to buy quite a lot of this radium water. He drank around 1,400 bottles of this radium water, and the result was the death of the cells in the jaw bones, and finally radiation anemia. And even more maybe famous case is the case of so-called radium girls. It was enterprise in USA who produce these parts of the watches and compasses So these arrows, numbers, scales, and these parts were painted with the paint containing radium. So the paint itself glowed in darkness due to the luminescence of this paint. And of course, it was necessary to put this paint on these tiny particles with brush. And girls or women, they are very careful with these actions. They have very good so hand precision. And when the brush is not very thin, the simplest way to make it thin, just to put it in the mouth to make it wet, and then you have a tiny edge, and you can draw these tiny particles. So due to this actions, due to these operations, a lot of girls, they had quite a lot of radium inside, and also very similar to the effects on the Epstein-Barr virus. They had a necrosis of the jaw bones, anemia, and it was one of the first cases when the professional union won the application in court, and this enterprise paid quite a lot of money to these radium girls. But today radium is known not for each, of course, also for some negative actions maybe, but today we know radium as the one medicine for therapy. So it is a radiopharmaceuticals that is used for therapy of bone metastasis, and at the moment I think it is the only one. And yeah, so radium then and radium now is quite a big difference, and we should so just point your attention that it's not a natural radium. Natural radium is radium-226 with quite a long half-life of 1,600 years, but for medical applications we use radium-223 that is produced either by irradiating particles, by charged particles, or by neutrons that you already heard yesterday and today. Another example, maybe just last of these past examples of the let's say misuse of ionizing radiation. It is so-called pedoscopes. So it is apparatus to look how the shoes are fitted to your feet. And so it's very convenient. You just put your foot in the shoe, and you look by using X-rays immediately how it fitted, so you can choose the correct or the best fitted shoes for your feet. So very nice. But of course, due to the action of X-rays and almost no shielding, the people who worked at these stores who used these pedoscopes, it was cases then they had this radiation disease, they had also anemia, and of course these pedoscopes were closed, and the application, but the last pedoscopes were found even in the late 70s of last century. So I would say that for a very long time, even then, everybody already knew about the negative action of the ionizing radiation, possible negative action. They were still in use in some US states, even in Sweden. But yeah, today, of course, they are not in use anymore. So the reasons of this, all these bad stories, of course, in the beginning, it was lack of the knowledge about the real action of the ionizing radiation on the how different amounts and different types of ionizing radiation effects on the living organism. And of course, when the safety standards were already released, the first safety standards were released in 30s of last century in Great Britain, but they were not safety standards. I would say it was recommendations for safety when using ionizing radiation sources. But in 40s and especially in 50s already, people make these safety standards that are mandatory for everybody who use sources of ionizing radiation. But even if we have safety standards, people can misuse sources of ionizing radiation. Maybe the most famous cases when people found some sealed sources, medical sources of ionizing radiation, and they broke them, and they had very intensive radiation due to the cesium salts or cobalt salts. And yeah, as a result, many people died or were injured. So again, just a reminder that different types of ionizing radiation interacts with the matter in different ways, and one of the result of these different mechanisms is the penetration ability for the matter. Alpha particles, they're heavy particles, they have very high charge, +2, so it's high charge for the particle. So they have very short penetration ability, very small penetration ability, very short ranges. Beta particles have larger penetration abilities, but still it may be a few millimeters in the solid materials. So if we are talking about the alpha and beta emitters, that means that if they're staying outside of our body, they don't possess, let's say, any danger. But if this alpha or beta emitters, if the daughter radionuclide can produce gamma radiation, then they have a problem, because gamma radiation has a high penetration ability, and thus if we have gamma source outside of our body, that means that gamma radiation can reach us and make some negative effects in our body. But from other point of view, if we put gamma radiation inside our body, that means that it can go from the body and can be detected. So if we use gamma emitters as radiopharmaceuticals, we can see where the gamma radiation is located in the body, and thus gamma emitters we are using for diagnostics. And as far as alpha and beta particles, they are accumulated totally, their energy is accumulated in the body. That means that we can use their energy to kill bad cells, to treat the cancer quite efficiently. So again, knowing principles of interaction of different types of ionizing radiation can give us some ideas on how to use this different radiation properly. And about action on living organisms, first of all, as far as in our body, around 70 to 80% it is water. Yeah, so quite a lot of water in our bodies. Then the first matter that interacts with radiation matter is water. And due to the radiolysis, due to the destruction, let's say, of water molecules by ionizing radiation, we can, not we, but quite a lot of radicals are produced from the water. And these radicals, these very active particles can react with the biomolecules, with ferments, with the membranes of the cells, with the DNA, and thus they can modify these biomolecules, and as a result, biomolecules will no longer work properly, and this will lead either to the death of the cell or to the mutation of the cell, and then the result can be different, either due to the negative mutation cell. I would say simple words. I will use simple words like cell will understand that this negative mutation is not good for the organism, and thus cell can initiate the procedure called apoptosis, or it is programmed suicide of the cell, and thus the cell with negative mutations will destroy itself, so the whole organism will not be affected, or if for some reasons this procedure is not initiated, cell can become a cancer cell, and with the whole other negative effects. So again, going back to the action of the ionizing radiation going back to the mechanisms of the interaction of ionizing radiation, we can divide all ionizing radiation on two parts: directly ionizing and indirectly ionizing. So directly ionizing radiation, it is radiation that brings the charge by itself. So it's charged particles. It can be electrons or positrons, or it can be heavy charged particles like protons, alpha particles, or other nuclei. Or it can be indirectly ionizing radiation that doesn't have any charge. So it is just electromagnetic radiation. Just a moment. So it can be electromagnetic radiation like X-ray or gamma rays, or it can be how it's called, particles with no charge, the neutrons. And this indirectly ionizing radiation can, with different actions, either it is electromagnetic interaction that you already know, this photoelectric effect, content scattering, or electron positron pair production, or due to the nuclear interactions that you've seen on Monday. I guess it was a presentation by Dr. Aliyev. So in all these actions, indirectly ionizing radiation will produce particles with charge, and then we have again the same Coulombic interaction of charged particles with matter. So as a result, always it will be interaction, direct or indirect interaction of charged particles with the matter. And we can use it either for detection of ionizing radiation, or to assess the energy that was deposited in the matter, so we can use it for calculation of the doses. So again, going back to the radiolysis of water, we can see that there are quite a lot of different processes. It's not the final equations. The total number of equations with water is around 100 different reactions. So just one molecule, initial molecule, and so many different products, active products from this simple molecule. And as I already mentioned, these active particles can interact with the biomolecules and change their properties that will finally affect on the let's say health of the organism. But how to assess how many particles are produced in these reactions? To assess how many particles are produced, we use the quantity that is called radiochemical yield. it is quite easy to understand the ideology of this term. So the radiochemical yield is just the number of particles that are produced by the some part of energy. So if you have, I don't know, 100 electron volts that are accumulated in the matter, and you produce 2 molecules or 2 radicals, or you destroy 2 molecules, so it can be in both directions, then you can say that your radiochemical yield is 2 molecules per 100 electron volts. And this number, molecules per 100 electron volts, is used very often in papers, in the research work, because it's quite convenient to use, because it's always some small numbers like 1, 2, or half, 1.5 molecules per 100 electron volts. Of course, we can recalculate it in standard units, and 1 molecule per 100 electron volts will be 0.1, let's say, macromole per joule. But yeah, it's not so convenient to use then 1 molecule per 100 electron volts. So both units are equal, so you can use what you like, because you always can recalculate one from another. But the indirect action, so of ionizing radiation, when water is produce all these active particles, all these radicals, is not the only way. Of course, there is also a direct effect of ionizing radiation, when ionizing radiation goes directly or destruct directly the DNA molecules, and at this moment DNA can be repaired. And in 2015 the Nobel Prize for chemistry was given for the work on the mechanisms of the reparation of DNA. And it is important for us because this reparation DNA process is also responsible for the for the response of the organism to the action of ionizing radiation. So it's the same processes. And actually, it is one need quite a small amount of energy to destroy the molecule or DNA molecule or other molecules like proteins or membrane cell. And sometimes it is called radiobiological paradox, because this amount of the absorbed energy that will result in the death of the organism will actually hit the body only by 1,000th part of the centigrade. So it's a very small energy, but still enough to kill the person. For the radiation protection, so it's sometimes radiation can really have a lot of negative effects. To protect efficiently and in proper way, we use 3 main principles of radiation protection, or 3 pillars of radiation protection. Is justification, LRA principle, so it is abbreviation of as low as reasonably achievable, and the 3rd pillar is those limits. So justification means that the use of ionizing radiation can bring more positive effects than possible negative effects in any application of ionizing radiation. In other words, if you can make your experiments or procedures without using ionizing radiation, do it. Yeah, don't use ionizing radiation if you can avoid it. So it's the justification. But if you have to use ionizing radiation, then you should use it as low as reasonably achievable. And these 2 words, reasonably achievable, is they are quite important. What does it mean? Of course, just imagine you have to make a diagnostic procedure for the patients with the radiopharmaceutical, this positron emission tomography, for example. And of course, you can use a very small amount of the radionuclide. But if you will take very low amount of radionuclide, you will not have enough signal that will go from the body. So the whole procedure will be useless. Yeah. So you use a very small amount of radionuclide, but you don't have any positive effect. Yeah. So it's useless. So you have to use such amount of radionuclide when you will have already some signal, some diagnostic, but not to take too much. Yeah? So it should be some balance between the result that you would like to achieve and the amount of the radionuclide that you will use. And to assess the possible effects on the human health of the used, as low as reasonably achievable, the used amount of radiation, we use doses and the limits of the doses. So in principle, there are pretty, I would say, a lot of different terms, and we will go through most of them. So there's some relationship between basic physical quantities, I would say fundamental physical quantities like absorbed dose. Then we have protection quantities. These quantities are written in safety guards, so in safety standards and safety documents. So what should be the equivalent dose, the limit of the equivalent dose? So these are protection quantities. Of course, we have some signal that goes from the equipment from our detectors, but the point that detector will never say you the energy of the particle or the amount of energy accumulated, because detector will only give you some response on the action of ionizing radiation, and it is your duty to interpret or to convert this response to some dosimetric quantities, because detector don't know about the energy of alpha particle. He knows how many electrons and other charged particles are produced inside the detector due to the action of ionizing radiation. Yeah, we can detect the this peak of the signal, the peak of the current that is produced due to the action of ionizing radiation, but detector don't know what the energy of alpha particle or gamma quantum has entered to this material. To make a calibration of the response and energies of gamma quantum is the duty of the operator. Yeah? So instrument will give you only the response of the detector, nothing else. So from the measured quantities, we can go to the operational quantities. So we can say, okay, this response means that the ambient dose equivalent or personal dose equivalent is this. And from these operational quantities, we can go to the protection quantities and say, are we above the limits or below the limits, etc. So, and we will start with these fundamental physical quantities, and the main quantity, I would say, it is the absorbed dose, because it is the energy that is absorbed in the matter, and it doesn't matter what type of ionizing radiation, directly ionizing, indirectly ionizing, doesn't matter. The whole energy that is accumulated in this material, in the matter, will be counted, and so the absorbed dose is just the amount of the energy divided by the mass of the object. So in standard units is joule per kilo, or we have a special unit for this. It's 1 gray, so named after Lewis Harrod gray. Another related to the absorbed dose unit or quantity is kerma, so-called kerma. So it's an abbreviation of kinetic energy released per unit mass. What does it mean? It means that when indirectly ionizing radiation interacts with matter, it produces some charged particles. And the energy of these produced charged particles is counted as the absorbed energy in this matter. So kerma is related only to the indirectly ionizing radiation, to the X-rays, gamma quanta, and neutrons. For other types of radiation, we used absorbed dose. So there is, I would say that if we have indirectly ionizing radiation with the energies less than 10 mega electron volts, that is typical for all the radionuclides. The gamma quantum that are released from the radioactive decay from the radionuclides is not above 10 mega electron volts. So in this range from 0 to 10 mega electron volts, I would say that kerma and absorbed dose will be equal for all types of ionizing radiation. So kerma is important when we use accelerator of the electrons, when quite a lot of X-rays are produced with quite high energy, much more than 10 mega electron volts. You've seen this special quantity that is called Bremsstrahlung. I've heard that different lecturers called it in different ways, but in German it is Bremsstrahlung. So Brems means breaking, Strahlung means radiation, and so this term come from this German words. And this stopping radiation, it is just electromagnetic waves with high energy, and the energy as high as the energy of the initial electrons. So if you have accelerators of electrons that gives you electron with energy, I don't know, 20 or 30 mega electron volts, that means that your stopping radiation, this Bremsstrahlung, will also be in a range from 0 to 20 or 30 mega electron volts. In this case, when we calculate the shielding, for example, thickness, then we already have to take into account kerma, not the absorbed dose. But if we are talking about the radionuclides, about the radioactive materials, kerma from the gamma radiation of radioactive decay will be more or less the same as absorbed dose. And quite old quantity that officially is not used today, it is radiation exposure dose. Maybe in especially, I don't know, in English textbooks, but at least in Russian textbooks, this unit, Röntgen, they are used quite often, and even now people, especially people, let's say, older than 50 years old, I would say, they still use these units, Röntgen, when then they're talking about the doses. Yeah, some micro Röntgen per hour. It's a typical dose or those unit that they use. Of course, today we are using another units. Today we use protection units that are measured not in Röntgens, but they are measured in sieverts. And what are sieverts? So first, before the sieverts, we can calculate the specific dose that is absorbed in the tissue. Yeah, this symbol T, index T means tissue. And for some application, especially for medical application, when Usually, ionizing radiation is focused on only one or organ or one section of organs. This absorb those in organ or in tissue very important, because we don't, not always, but normally we don't irradiate the whole body, some part of the body. But as it was discovered around, I don't know, let's say 100 years ago, that different types of radiation have different effects on living organisms. And to take into account these different actions of different types of radiation, the new quantity equivalent dose was not invented, but was suggested. And what the equivalent dose? Equivalent dose, it is the same absorbed dose, this absorbed dose measured in gray, but multiplied by the Wien factor that depends on the types of radiation, or again, in all the textbooks, it called the quality factor of radiation. And you can see that for photons, that means X-ray and gamma quanta, this Wien factor is equal to 1, but also it is equal to 1 for electrons. That means for beta radiation, or in electrons in accelerator. Why? Because again, the result of action of the electromagnetic radiation will be electrons. And then electrons with high energy will interact with the matter. Again, just remember the photoelectric effect. Then the whole energy of the gamma quanta goes to the electron, and electron now has this high energy and interacts with the matter. So from this point, photons and electrons, they have almost equal effect on the living organisms. So they have this Wien factor equal to 1. Yeah, and I forgot to say that the equivalent dose now measured in sieverts. Yeah, so this sievert. And you can see that alpha particles, they have much higher Wien factor. That means that when alpha particles interacts with our body, they are 20 times more dangerous or hazardous than gamma quanta or electron, when we are talking about the same energy deposited. Yeah, because don't forget about the absorbed dose. Neutrons, they have quite complex dependence of this Wien factor. There's maximum in the energy range of 0.5 to 10 to 2 mega electron volts. In this maximum, Wien factor reaches 20, but yeah, it ranges from 2 to 20 depending on the energy of neutrons. And now, again, it was discovered that not only different types of ionizing radiation have different effects on our organisms, but also different types of different parts of our organisms, they have different sensitivity to the ionizing radiation. So to assume this different sensitivity, people use the effective dose. Effective dose also measured in sieverts. But in this case, you can see that it is product of the equivalent dose. So we already take into account Wien factor for the certain types of ionizing radiation, so equivalent dose. But also it is product of equivalent dose and the Wien factor now for tissue, yeah, for the specific organ where the energy is deposited. So, and depending on the organ or tissue, it was proposed to divide them on these 4 groups. The most sensitive organs are bone marrow, so where the blood cells are produced. So it is so in principle, how to not to remember all these names, but just to understand why different organs or tissues have different sensitivity, you should remember only one simple fact that the most sensitive period in the life of the cell is the process of dividing, one cell onto two cells. If you have in organ a very how to say, if your cells are dividing very often, like production of the blood cells, it's always you produce more and more cells. That means that very often the cells are dividing. Or if you produce cells like in breast or in other organs, I would say. So if you have very often process of this division of the cells, of this dividing of the cells, then the more sensitive will be your tissue, your organ. So in these organs, you have very often dividing of the cells. There is another representation of our body with these four groups of different tissues. One point that all these vein factors, they are relative units. That means that we take the whole body as a one unit, and then relative to the whole body, we say that these or those organs are more sensitive or less sensitive. Together, if we calculate all these vein factors together, they will give us one as a whole body. So it's just relative units. And now, what are the protection units in absolute values? So for, again, it depends on the country. Of course, there are some recommendations from the International Union on Radiation Protection, but it's their recommendations. Again, any country can take the values what they like, what they want. So in, for example, in Russia, we have limits for people who work with ionizing radiation, with radioactive materials or ionizing radiation. So it's 20 millisievert per year, but in average for 5 years. And in one single year, it should be not higher than 50 millisievert. That means that you have 5 years, and in 1 year you can have, for example, 50 millisievert or 40 millisievert, but in for following years, in total, you cannot have more than 60. If you have 40, not more than 60 millisievert. You can divide it by 4 years, so it will be not 20 but 15. So again, for consequent 5 years, it should be in average not more than 20 millisievert for people who are working with ionizing radiation. It is for the whole body, and for skin and for hands, this can be even higher. So in Russia, it's not 500 but 300 millisievert, but still much higher than for the whole body. And there is one interesting point that for public, for normal citizens, let's say, the average dose should be not higher than 1 millisievert per year. But what is interesting that in this value, we don't use the doses that are accumulated due to the medical procedures. And we will see why. So This is just a calculation. So 20 millisievert per year, it's quite difficult to understand. I'm now working with the source of ionizing radiation. What is the limit of the ionizing radiation just right now, per hour or per day? Yeah, in Russia again, we have by regulation, so our working regulation says that people who are working with the ionizing radiation, they are working 1,700 hours per year. So, and if we divide these hours, this 20 millisievert by this number of hours, we will obtain 12 microsievert per hour. So it's, if you work constantly with the same source the whole year with the same source, so then ionizing radiation dose should be not more 12 microsievert per hour. Of course, it's just some number, how to say it, to see if the dose is already high or it's still okay, I would say. On the second floor, there is watches that show not only time but the dose rate now outside of our building. And if you have seen the normal dose rate during the day, it is 0.1 microsievert per hour. So it's normal radiation background in Moscow. Of course, depending on the location, it can be higher or lower. For example, in Moscow, I would say it's quite a low natural background. In 1 year, it is around 1.5 millisievert from natural background. Yeah, good point. I forget to say that in all this number, we don't we subtract the natural background. Yeah, so it's without natural background. So in Moscow, it's around 1.5 millisievert natural background. But in average on our Earth, it's around 2.5 millisievert per year. So we are living, I would say, in very low radiation region. But yeah, so this number is just like a signal if it is already high radiation or it is still normal radiation. Don't take it as a limit of the dose rate to work. But it's nothing here. Okay, so I will just mention again the medical procedures. For example, one procedure of computer tomography using X-ray tubes. Yeah, so it's X-ray technique. So depending on which part of the body we are scanning, doses can be from 2 to 30 millisieverts per one procedure. So and just imagine that one annual dose is around 2 millisievert, I would say, and one procedure on computer tomography will give you several annual doses. So again, going back to these 3 pillars of radiation protection, again, we are starting from justification. If these procedures, medical procedures, will give more positive effects than possible negative effects, then of course they have to be done. So this justification principle. Okay, so protection quantities more or less understandable. Now, very difficult part, operational quantities. It is so for operational quantities, we use so-called ambient dose equivalent and personal dose equivalent. So ambient dose equivalent means that imagine that we have different sources of ionizing radiation, so we have quite a difficult radiation field in our building, in our, I don't know, room, in our hall. Then to calculate precisely, it is possible, but to make it more precise, I would say, people use special phantoms. So it's material that is made of plastic which composition is very close to the composition of tissues. So it's called tissue equivalent material. And we put this phantom either in mathematical model, or we put it in just real experiment. And we measure, either calculate or we measure what will be the dose on different depths in our phantom. And so for different applications, for different protection quantities, we use different depths. For example, if we would like to calculate the protection quantity for the whole body, then the depth will be 10 millimeters. So more or less the whole radiations will be absorbed at this depths. Let's say, for example, for eye lenses, this depth will be 3 millimeters, and for hands it will be 7 millimeters. So another phantom, it is so-called slab phantom. So it's not a sphere. So sphere may be a good representation of the body, but not perfect. So this slab phantom now also used for calculation of the protection quantities from the operational ones. So the slab also made of tissue equivalent plastic with these sizes. So the sphere with the it's not a radius, its diameter should be, so it's a mistake. 30 centimeters, and slab with the sizes 30 and thickness 15 centimeters, so representing human or let's say sensitive part of the human bodies. And yeah, these depths, as I mentioned, they're used to calculate different protection quantities. So in principle, if we know what is the source of our radiation, for example, again, for medical application, if we are using gamma radiation, it normally cobalt-60 or cesium-137. So if we know which radionuclide we are using, or what is the energy of the gamma radiation or X-ray radiation is used, we then can calculate the dose rate from this simple equation. So this coefficient, the gamma constant or Kerma constant, depending on which units we are using, either it is Grays or it is Röntgens, depending on what we are using as a measured units. This constant is called with different names, but it is constant. Again, we can take it from just database for given radionuclide. We easily find the value of this constant. And if we know the activity of our radionuclide and the distance from this source, then we can easily calculate the dose rate. And dose rate, so it's a dose per time. So if you know how much time we are spending on this distance from the source, then we can easily calculate the absorbed dose. But these constants, they are given not for tissue, they are given for the air. And thus we have to recalculate this absorbed doses calculated for air to the absorbed doses calculated to tissue. To do this, we have to use absorption coefficient for the gamma radiation, and this absorption coefficient in tissue and in air. But you can see that for quite a wide range of gamma radiation, and I would say already X-ray radiation, this relationship between the absorption coefficient in tissue and in air, they're in very narrow range from 106 to 1.12. So in general, when we need to make quick calculations, we just take the average value 1.09 to recalculate these doses from air to tissue. And this example on how the kerma is different from the absorbed dose, because kerma, again, kerma, it is the energy of the charged particles produced by the action of indirect ionizing radiation, of X-rays, of gamma radiation, for example. In this case, you can see that when gamma radiation interacts with matter, charged particles are produced, and these charged particles, they are used to calculate kerma. But gamma rays or X-rays, they have quite a big penetration ability. So that means that they can penetrate quite in big distance inside the matter without any interaction, and only at some distance they produce these charged particles. That means the deeper the gamma radiation goes in the matter, the more probability that this radiation is absorbed and produce charged particles. That means that kerma, it's not so. It's interesting that if we will look on the how the flux of the gamma radiation is decreasing, then we will see that this flux will decrease from 100% to, I don't know, 50% or lower. But this decrease will start from the very first point, from this, let's say, 0 point, and then it will be exponentially decrease. But kerma, this energy accumulated in the body, is increasing at the first point, and then it is, I would say, more or less constant. And then it's decreasing as the amount of the gamma radiation is decreasing. So this picture you've already seen. This is a difference in the production of these doses by photons, by gamma rays or X-rays, and by charged particles. If photons, they produce this kerma, you see this dose is increasing in the beginning, but then decreasing due to the decrease of the flux of the photons, so according to this exponential law. But it will be never zero, because exponent will never reach zero value. It will infinitely go to the zero, but never reach zero. But protons or any other particles, charged particles, electrons or protons or other alpha particles, they have a limited range. So, and what is good for heavy charged particles, they lose almost all the energy at the end of their range. Thus, the maximum of the energy loss or energy accumulation will be at the end of the range. And thus, it can be used for proton therapy. Again, the energy of protons, rather high, from 70 or to 200 to 250 mega electron volts to have enough penetration ability. But they're stopped at some point. If we have proton flux going from somewhere here, they will not go for longer than this distance. Thus, these tissues will be not affected by the action of the ionizing radiation. Instead of use of gamma knife or X-ray knife, when we have fluxes from several points, and even the tissues that should not be irradiated, they will be irradiated, because the flux of photons will not stop so easily. So this different mechanism of interaction will give you information on what will be effect on the living organisms of your ionizing radiation. And now about the effects, different effects depending on the doses. We can divide them by deterministic effect and stochastic effect. So deterministic effect, they're typical for high doses that are accumulated in short period of time. And as far as it is very high doses that accumulated in short period of time, the organism, even if we have this mechanisms for reparation of DNA, of the fighting against the negative action of ionizing radiation, the concentration of the effect is so high that our organisms cannot fight anymore, and depending on the dose, we will see different direct effects of ionizing radiation, from hair loss to some to skin damage, cataracts, and the final effect is just a death of the organism. So it is for high doses accumulated in short period of time. But normally we, of course, working with low doses, and we accumulated during the whole our lifetime. And in this case, we are talking about the stochastic effect, when we observe not the direct effect, so it's not a probability direct effect dependent on the dose, but in case of stochastic effect, we are talking about the probability of having some effects dependent on the dose. And again, this classification of different effects, radiation effects on organism, it can be some somatic effects, so it's effects on our organism, or it is effects on the population after us, so on our children. But if we are talking on somatic effects, on the effects on our bodies, so again, we can divide them on earlier deterministic effects, again, this radiation sickness, etc., or these late effects that are stochastic, and in some cases deterministic. So what, how we can collect the statistic for all these effects, and for the numbers, let's say, which dose will bring which risk to get cancer, for example. So there are three gold standards, let's say. One is the people who survived the nuclear explosions during the Second World War. So it was quite a good reconstruction of the doses depending on the distance from the epicenter of the explosion. And of course, all these people during their whole life, they had quite a good medical care, medical examinations. So there is a statistic on each person. We know which dose approximately had at this moment, and during the lifetime, what are effects of this dose. So it's around 80,000 people. Another data set is people who are work on nuclear power plants and nuclear fuel cycle facilities, production of nuclear fuel, reprocessing of nuclear fuel, management of radioactive waste, etc., etc. And another data set is patients and actually doctors who are working with ionizing radiation for medical application, diagnostics or therapy. So from all these data sets, it was discovered that there is a linear relationship between the risks of getting cancer and the dose accumulated during the long period of time. So it is a linear relationship. The higher dose, the higher the risk of getting cancer, not the effect. Yeah, it's important to see that in this case, we have a probability, not the direct effect. But you can see that in very low doses, there are three different models. Why they are three? Because in this very low, in this range of very low doses, it is very difficult to say statistically to divide the effect of the additional doses and the doses from the natural sources. So it is unknown if it is effect of just a natural background, so it's natural risk, or it is additional risk of getting these low doses. So the linear model is quite simple. Yeah, we have a statistic from this free data set, and we just made this fitting to the 0.00. So it is non-threshold from this linear model goes from 0 point, and any addition of the doses will causes some increase in the cancer risk. Yeah, so non-threshold model, linear model. There is another model called hormesis. You see that in this low doses in this region, the risks are negative. That means that it is positive effects on our health. And hormesis is a known model when we are talking about the poisonous materials that in very small concentrations, some poisons can be used as a medicine. It is a known fact. And what people are saying about the hormesis effect of the ionizing radiation, that these small doses, they stimulate our immune system to fight against the effects of ionizing radiation. So the small doses stimulate always immune system, and that's why we have a positive effect of these small doses of radiation. And people with this effect, they are talking about the health of the positive effects of radon baths and other procedures. Of course, it's not correct because it's statistically there is no effect. Another model, a supralinear model, says that no, and at this such doses, additional doses, our organism cannot see them above natural background. So that means that our organism has these additional doses, but cannot see the effects. So no additional immune system, immune response is activated, and thus negative effects, they are accumulated, but our organisms cannot see it. Thus, the negative, in total negative effect is even higher than they think, when we think. So again, there is no confirmation, no proofs about this model. It's just not speculation, it's debates on the effects of this low doses. If you would like to just know about the numbers when it is already when we should talk about the deterministic effect, this acute radiation sickness, for example. So acute radiation sickness is around 1 gray. So why we use here gray, not sieverts? Because you've seen that for photons, for gamma rays, sievert and grays, this Wien factor is equal to 1. So sieverts and grays, they are, I would say, the same. And to get this such high doses, it is possible in normal cases only due to the action of gamma radiation. So that means that sieverts and grays in this case are the same. So you can write here gray or sieverts, it will doesn't matter. So acute radiation sickness dose is around 1 gray. Of course, all this depends strongly on the condition of the person. Yeah, if the person is very healthy, then this dose can be a bit higher or not. Again, it depends on the how good this reparation DNA process
is working in the organism. So this dose is statistically around 1 gray, but don't take it as a fixed value. It strongly depends on the human health. But as a threshold for the deterministic effect, we use this number, so it is 100 millisieverts or milligray. Again, for gamma radiation, it's the same. But again, it is dose that is accumulated for the short period of time. If we are talking about, I don't know, 5-year period of time, then it's not deterministic effect. And the lethal dose is around 10 grays, and this number I used to calculate this radiobiological paradox. So again, gray, it is 1 joule per kilo. We can assume that our body is water, so we know the heat capacity of the water, so we can recalculate what will the increase in temperature be after getting 10 joule per kilo. It will be not the 1000, of course, it will be 2000 centigrades, but more or less the same order of magnitude. To control the doses, to control dose rates, we use different kinds of dosimeters. There's still quite a lot of different investigation and research work on the dosimeters. I would say that the most popular dosimeters, they are thermoluminescent dosimeters. It is wearable dosimeters with this, let's say, tablets inside, and these tablets, they are made of the material, sometimes, very often, with the lithium fluoride, because in average it will give the same average charge as a tissue. So it's light elements like carbon, oxygen, nitrogen. Yeah, in average it will be close to the tissue. That average, that's why it is very good materials to calculate this protection quantities. So what the principle? When getting the additional energy, there are some defects in these crystals, and when you hit these crystals, they emit lights when these defects are disintegrated or annihilated. By heating, that's why it's thermoluminescent dosimeters, by heating and by detection of the emitted light, you can say what the energy was accumulated in this tablet, and thus you can calculate then the personal dose. Another materials, it is optically stimulated luminescence. Again, you have material, some crystal made of current or aluminum oxide, and again it accumulates energy, and then when it's irradiated by laser, it emits light, and light again detected, and you recalculate it to the personal dose. Or it can be ionization chambers, so it is gas chambers that are very sensitive to the action of ionizing radiation. By directly detecting the current in these ionization chambers, you can get information about the doses. Some other dosimeters, chemical dosimeters like free-K dosimeters, it is solution of iron 2, and depending on the dose, iron 2 converted to iron 3, and by changing the color of the solution, by measuring it by spectrophotometer, convenient spectrophotometer common, you can say what dose was accumulated in this ampoule. Other types of such dosimeters that are used for example, for calibration of the accelerators. Yeah, this I don't know if you see good. this green color in this plastic, it is the action of the accelerator of electrons. So you can see how homogeneous the flux of the electrons from this accelerator. So it's quite so you can see it quite clearly. Or this plastic dosimeters, polymers, that are used also to simulate the dose distribution on the different parts of the body by the action of the certain type of the radiation. So they're used quite widely to simulate the doses on typical, not typical, but specific parts of the body. Different dosimeters for doctors used for when treating patients, for eye lens, for fingers. You can see this, all these dosimeters on different parts of the doctors. And of course, one important point, that these dosimeters, they are so-called accumulated dosimeters. So you cannot see immediately what the amount of those you already had. But of course, we also have the online dosimeters that show you the dose rate immediately and accumulated doses. But they are good only for, I would say, high dose rates when it's really some extreme conditions. And then you need to see immediately that there is some radiation fields with the dose rates above the limits. But these accumulating dosimeters, they are very sensitive for low doses. Again, for example, we change these dosimeters once in 3 months. So for 3 months, it's accumulating low doses, and then we can see some response. Not sometimes it's very close. In many cases, it's very close to the background. So that means that even if we are working with some radiation sources, very often we work with such a small amounts of radiation that even such dosimeters cannot see it. And how to protect yourself from the ionization from ionization source. So first of all, of course, it's time. Spend less time with ionization source. If you cannot do it, try to go as far as you can, because the dose rate decreases as a squared distance. So if you increase the distance 3 times, the dose rate will decrease 9 times. So it's very efficient. So if you can go from the ionization source, it's good. But it's also true for any kind of sources that spread any electromagnetic waves. Even the for our cell phones, this apparatus which send the signals to our cell phones, the power also decreases as a square distance. So they're quite far from us. That's why the energy that goes to our cell phones are really very, very low. But if you come closer, of course, the energy will be quite high, but not ionizing energy from the cell phones. Just a reminder. And if you don't go for infinite distance and to decrease time to the 0 seconds, then you probably will need to use shielding materials. Yeah? And for gamma radiation, we remember that the heavy materials have a very has higher probability to absorb gamma radiation due to the photoelectric effect. For example, when the whole energy of gamma quantum will be absorbed by the electron, that means, just imagine that whole energy of gamma quanta accumulated to the electrons. That means that there is no more gamma quanta. Yeah? So it's very efficient, and the probability of photoelectric effect is very high for the heavy materials, for dense materials, and that's why we often use lead, yeah, or lead glass. It's comparison of the thickness of the lead glass and the common glass, so to decrease the gamma flux on the same value. So the thickness of the lead glass, you can see, is much smaller. And for production of radionuclides, especially if we are talking about the nuclear reactors, then probably we will need to use the hot cells with these manipulators and very thick beton and steel and lead between the target and between us. So in summarizing how different materials can stop different types of radiation, again, for alpha particles, if they're outside of our body, it's just a normal personal protection systems like gloves, like some other protection. I forgot how it's called. Okay, ingestion protection. For beta particles, it is important to use light elements to protect against beta. So it is aluminum or some organic glass or some polymers or something like this, light materials, because if we will use heavy materials for protecting against the beta, then we will produce a lot of this stopping radiation or this Bremsstrahlung. So no heavy materials for beta radiation, or you need to calculate it properly. For gamma radiation, again, it is lead or very thick concrete constructions. And for neutrons, we didn't talk a lot about neutrons, but neutrons, they are decelerating very efficiently by light atoms, by hydrogen, first of all, and we can use some additions like cadmium or boron to catch the neutrons. So this picture was taken from one website. I think it's a very nice representation of how different materials can be used for protection. And again, for beta emitters, we use light elements for containers for beta emitters. Usually it's plastics. So at synchrotrons, again, it is either thick concrete blocks. Sometimes it is concrete blocks made of special concrete with the addition of heavy elements like barium. So in concrete, normally you have a lot of calcium and barium that is much heavier than calcium, but by chemical properties, it's more or less the same. So you can substitute calcium by barium in your silicates in concrete, but the protection against the electromagnetic radiation will be much more efficient. And of course, for medical facilities, I think that you've seen these rooms for personnel when going X-ray examination with these rooms with the special glasses, either lead glasses or just thick glasses. We wear quite often these clothes with lead pasts when doing, I don't know, for example, teeth X-ray tomography or other examination. But if we are talking about radiopharmaceutical, there are special equipments like these syringe shields of, in this case, it's tungsten, or it can be lead with the lead glass. And yeah, typical protection for the sources when people prepare some radiopharmaceuticals. It's one of the examples. So I think that is all for today's lecture. So you should know how to protect yourself against the ionizing radiation. So if you have any questions, I will be glad to answer. So thank you. Yeah. Well,
yeah, thank you. In the slide where you showed the yearly doses for workers, for regular people, and for apprentices, you included a line about the eye doses, and it said that it's the same as the adult to protect the eyes, but it didn't make sense to me really. If you make the dose for apprentices more, how does it protect the eyes?
protect the eyes. I don't know. What do you mean protect the eyes? That means the sensitivity of organ is the same. So it doesn't matter. Or what do you mean again?
I just didn't understand the annotation that that slide had.
Just a moment. Let's go this. Here, yeah?
Yeah, C.
I can look in this source. I know the book where I take it. What? Yeah. Of course, it's true, but I cannot know how to answer why it is the same.
It's not long distance like this. We have filters for our eyes. You know, it's not glass, but I don't know what is the exact composition of them. But it's like this. There's a table.
Okay, sure.
This. That's why they are the same limits.
Oh, so because there is protection,
yes,
the limit is the same. Yeah, thank you.
Okay. So are there online questions? Okay, but it's interesting questions. I will look closer to this, Willis. But thank you. Any more questions? Yeah.
So it might be a silly question. Thank you for the very nice presentation, by the way. It might be a silly question, but I've read some articles before that I don't know how credible they are. They mentioned active protection against ionizing radiation, in the sense that if you can't avoid the radiation in any way, for example, if you're on a spacecraft or something, they come up with this idea that they don't protect against the radiation, they protect against the formation of the very dangerous oxidative species, some kind like diethylamine and other scavengers for these particles. What do you think about this? Is it a scientific thing, or is it just some bogus that...
No, it is scientific thing, of course, and these radio protectors they are used not only for people who work in space, but also for patients as well. So radio protectors, it's normal idea. So it's a scientific idea, and there are quite a lot of studies about them. They can contain some sulfur because sulfur interacts more rapidly with these active particles, with radicals. Yeah, it's okay. Yeah, maybe you've heard this idea about using alcohol for protecting ionizing radiation. So in principle, it also a working idea if you drink alcohol before working with ionizing radiation. But if somebody calculate how much alcohol you need to drink, and it means that it will be more alcohol in your blood than blood. So it doesn't make any sense. So because alcohol also interacts with radicals quite rapidly, but its concentration should be very high, so it doesn't make any sense. So don't drink. Then don't drink. Okay. Yeah. Any more? Yep.
Thank you thank you very much for the presentation. So my first question is the shield used in protection. Is it different from diagnostics and therapy? Do you have difference in it? The shield used?
In principle, not. It depends only on radionuclide that I used, and the calculations will be the same. But you just need to know what will be amount, maximum amount.
Okay.
Yeah, but calculations will be the same.
Okay, so what should be the ideal thickness of the shield? The ideal thickness.
There is no
ideal.
It's always specific calculation for specific room, for specific radionuclide. Yeah.
Okay. And also, how often do you check the lead apron? How often do you check it for you to check for leakages, maybe to check if you are safe when wearing it? How often do you check it?
There is some regulation on it for even for these wearable clothes with the lead parts. They should be checked, I think, once a year or something like this. Yeah.
Okay.
But for the equipment, normally we have radiation control and every day. So you see if everything is clean, if there is no leakage. But again, it depends on the not only on the regulations, but on the also on the rules in the company. So you write all the instructions, and you can write every hour. I don't know. Depends on. Yep.
Radiation. I can understand how they cause cancer or skin damage and so on. But what does it means when we say radiation anemia?
Anemia?
Yeah.
Yeah, it's cancer of the blood cells.
You mean it kills the red blood cells, and then you have a deficiency of the red blood cells?
Red process?
It kills the red blood cells, and then you have a deficiency of this. Okay, that's one question I have. The other one is, sometimes when you have higher doses, unless some treatment has been made, like in the case of 3 to 5 grays, some kind of intervention has to be done, yeah? So what are these interventions usually given to people who are exposed to higher doses of radiation?
You mean what kind of help or medical care? Or of course, first of all, this immune medicals to increase the immune response to this to the action of ionizing radiation. But what else they're doing? Of course, they have some standard medical process, but I don't know the details actually. I don't know the details what they're doing. I think the main idea is to protect the rest, to relax the people, because in these cases not a lot of procedures can be done to help. Yeah. Any more positive questions? Maybe. Okay, if not the case, then we finish for today with the presentations, and see you tomorrow.
Thank you very much.
Yeah, thank you. Oh, I will.
Because you are busy, I don't want to miss this opportunity.
I will ask my colleagues. They told me that will be maybe on Friday. I hope so. Yeah.